In this video, we're going to learn about logarithms. Now, just as a reminder, when we learned about exponential functions, we saw that they had graphs that look like this. One thing to note is that exponential functions are one-to-one functions. This is because they pass the horizontal line test. If we draw horizontal lines through our graph, we see that each of these horizontal lines will cross our graph just once. So again, for exponential functions, we see that they pass the horizontal line test, which means they are one-to-one functions, and what we learned is that one-to-one functions have inverses. Their inverses are what we call logarithmic functions. If we want to know what a logarithmic function looks like, all we have to do is take the mirror image of the exponential function across the line y equals x. So the inverse to the exponential function would look something like this. We'll label this f inverse, and remember we call the inverses to exponential functions logarithmic functions. Now a logarithm is essentially the operation that's being performed in the logarithmic function. Specifically, the logarithm with base a of a number x is the number y such that a to the power of y is equal to x. Now, when we write logarithm with base a of x, typically we use the following symbols. Log with a little subscript a of x. Now, if the answer to this logarithm is the number y, this means that a to the power of y is equal to x. So again, if we take the logarithm with base a of some number x, essentially we're looking for the exponent so that when I take the base and I raise it to that exponent, we end up with x. Let's take a look at some examples to familiarize ourselves with this operation. So what we're going to do is look at some logarithms. In example A, we want to compute the logarithm with base 2 of the number 16. So to compute this logarithm, we want to think to ourselves, 2, the base, raised to what power gives us 16, the number that we're taking the logarithm of? Well, we know that 2 to the 4th power is equal to 16, so that's why the logarithm with base 2 of 16 is equal to 4. So again, the answer to our logarithm is the exponent that we raise our base to so that we end up with 16. Let's try another one. In example B, we have log with base 5 of the number 25. To compute this logarithm, we want to think to ourselves, 5, the base, raised to what power gives us 25, the number that we're taking the logarithm of? Well, we know that 5 to the second power is equal to 25, so the logarithm with base 5 of 25 is that exponent 2. The exponent that we raise 5 to get 25 is our answer to the logarithm. In example C, we have the logarithm with base 4 of 1 over 64. To compute this logarithm, we want to think 4, the base, raised to what power gives us 1 over 64, the number that we're taking the logarithm of. The fact that we have 1 over something should indicate that our power should be a negative number. So we can start by thinking 4 raised to what power gives us just 64. And then all we have to do is turn that number negative. Well, 4 to the third power gives us 64. So if we do 4 to the power of negative 3, according to our exponential properties, this is 1 over 4 cubed, which is 1 over 64. So we know that the logarithm with base 4 of 1 over 64 is going to be that exponent, negative 3. Let's try to do a few more examples. In example D, we have the logarithm with base 3 of 27. So in your mind, you should be thinking, 3 to what power gives us 27? Well, the answer would be 3, since 3 cubed gives us 27. Next, in example E, we have log with base 7 of 1. So you should be thinking, 7 to what power gives us 1? Our answer here is going to be 0, since 7 to the power of 0 is equal to 1. Next, we have log with base 2 of 1 over 32. So in your mind, you should be thinking 2 to what power gives us 1 over 32. Because we have 1 over something, we should have a negative exponent. So you can first think to yourselves, 2 to what power gives us just 32? Well, 2 to the fifth power gives us 32, so our answer here is going to be negative 5, since 2 to the negative 5 is 1 over 2 to the fifth power, which is 1 over 32. And in our last example here, we have log with base 6 of 6 to the eighth power. So in your mind, you should be thinking 6 raised to what power gives us 6 to the eighth power. We see here that our number inside the logarithm is already written in the form 6 to some power, so the power is written here. So the answer to this logarithm is 8, since 6 to the eighth power is what gives me 6 to the eighth power. So this is how we take the logarithms of numbers. So next we're going to talk about some basic properties of logarithms as well as some notation. In our properties here, we're going to be using the letter a. Let's assume a to be some positive number that's not equal to 1. Our first property tells us that when we take the logarithm with base a of the number 1, this is always going to equal 0. This is because when we do this logarithm, we're thinking to ourselves, the base a here raised to what power gives us 1. And we know that for any number a, if we raise it to the 0th power, we always get 1. So the reason for this logarithm is because a to the 0th power is equal to 1. Our second log property is log with base a of a is equal to 1. When we think about this logarithm, we're thinking to ourselves, a raised to what power gives us a? Well, we know that any number raised to the first power is itself, so a to the first power gives us a. So that's why 1 is the answer to our logarithm here. Our next two properties show us why exponentiation and logarithms with base a are inverse operations of each other. We have the property log with base a of a to the x is equal to x. This property here we saw in our last example on the previous page, where we have log with base 6 of 6 to the eighth power. The answer to that logarithm was 8. In this logarithm, we're thinking to ourselves, the base a here raised to what power gives us a to the power of x. Since the number that we're taking the logarithm of is already written in the form a raised to some exponent, the exponent here is the answer to our logarithm. Another way we can think about this property is that if we start off with the number x and we exponentiate it with base a, and then we follow that up with the operation of taking the logarithm with base a, we see that those two operations cancel each other out, giving us the number that we started with. So again, this is why we say that exponentiation and logarithm with base a are inverse operations of each other. They undo each other. Our next property essentially says the same thing, only we're doing the operations in the other order. If we take a number x and we first take the logarithm of it with base a, and then we follow it up with exponentiating this expression with base a, those two operations are going to cancel each other out and give us back x. Let's take a look at an example of this. Let's say we start off with the number 8, and let's take the log with base 2 of that number. Next, let's follow this up by exponentiating this with base 2. So do 2 to the power of log with base 2 of 8. Now, according to our property, the two operations, the logarithm and the exponentiation, should cancel each other out, and we would end up with the number 8. But let's think about why. When we do log with base 2 of 8, we're essentially thinking to ourselves, 2 to what power gives me 8? Well, that power would be 3. Now, what are we doing with that 3? We're doing 2 to the power of 3. And so of course that's going to give us back 8. So again, our last two properties tell us that exponentiation with base a and logarithm with base a are inverse operations. These operations will undo each other. It's kind of like how addition and subtraction are inverse operations, or multiplication and division are inverse operations, or the operations of cubing and taking the cube root. Those are inverse operations. This concept will be important for us when we try to solve equations involving exponentials and logarithms. Now, before we close out this video, I want to point out some notation that we use involving logarithms. So sometimes you'll see a logarithm, but there's no base written as a subscript. When the base is not written, it usually means we're doing logarithm with base 10. For example, if we see something like log of 100, we see that there's no subscript written here to indicate the base. This means we're working with base 10. And so, to compute this logarithm, you want to think to yourselves, 10 raised to what power gives me 100? Well, 10 squared gives us 100, so the answer to this logarithm is 2. Again, this is because 10 to the power of 2 is 100. Also, I'll point out that on your calculator, you'll see a log button without a specific subscript. This means that whenever you press that button, you'll be doing logarithm with base 10. Our next bit of notation is that if the base of the logarithm is e, which is an irrational number, kind of like pi, then we write ln of x instead of log with base e of x. This number e is called the natural exponent. It shows up in natural ways when we work with exponential things, kind of like how pi shows up naturally when we work with circles. Now, when we do logarithms with base e, we call it a natural logarithm. That's why we use ln to indicate the operation. The ln here stands for natural logarithm. So in this video, we learned what a logarithm is, we learned how to compute logarithms, and we also learned some basic properties of logarithms.